strength or energy. And just like the last one, which was, so we actually did a calculation for a pretend process for a reaction in which you break all the bonds and then remake all the product bonds. Like that was not a process how it actually occurs, but it actually works out to be a good estimate of delta H reaction for covalent bond reactions. This is going to give us a good estimate of ionic bond strength or energy, but it is not a process that you can actually do. And we're going to use Hess's law. And it's going to be a very big example of Hess's law. And it goes something like this. Given the following information, construct a Born-Haber cycle showing all reactions and their energies to determine the lattice energy of strontium chloride. Also include how the reactants and products cancel out, just like the lecture outline video. So from the lecture outline video, when you're going to add up all these reactions plus the lattice energy reaction to make what's called the delta HF naught formation, for strontium chloride. Sorry, I cut and paste, but I forgot to cut and paste some of the things. So for strontium chloride. And so my process for doing this writes the delta HF reaction for strontium chloride at the very bottom of the page. And that reaction looks like this. Put strontium chloride solid on the product side. And then the reactants are going to be these two elements in their lowest energy forms. What that means is, so strontium solid plus chlorine gas. And the product for a delta HF reaction always has a 1. And then you can have fractions over here. We don't need fractions this time because this reaction is perfectly balanced. Okay, so then what you do is you start with one of your reactants all the way at the top. And you're going to do two things. You're going to turn the reactants into gases. And then you're going to turn the reactants into gaseous ions. Into gaseous ions. And so strontium starts as a solid, so we'll turn it into a gas. Going from a solid to a gas is called sublimation. And delta H reaction for the sublimation process is 148 kilojoules per mole. And I will give you all of these reactions and the delta H values for all of them. And in fact, if you remember from the lecture outline, I said that I would give you even more information. I would give you the layout if this shows up on your next exam or the final. We will see. But then, so turn the reactants into gases, then into gaseous ions. The next one says, take strontium gas, turn it into strontium plus 1 gas. And to do that, that's a reaction called the ionization energy, or the first ionization energy. And we write ionization energy reactions. Strontium gas goes to strontium plus 1 electron. And this was in lecture outline 8. And so this was in a previous lecture outline. And so we know how to write this reaction, hopefully, or we will look it up. Delta H for this process, which is delta H IE1, is given as 549 kilojoules per mole. And let's pause for a second here. These numbers are positive. That means that these two processes are endothermic. It takes energy to do them. And we're not surprised by that, because turning a solid into a gas, you have to separate the atoms very far apart, and it's going to take energy to do that. And then here, removing an electron from every single atom requires energy, and it's just a matter of how much energy. Okay, so then we're going to make these into gaseous ions that we're used to seeing. I guess I can add that we are used to seeing with charges that we are used to seeing. For example, so strontium, we're used to seeing it with a +2 charge because it's in group 2. Potassium, we would make that into a +1 charge. And chlorine, we're going to end up making it into a -1 charge for this example. So we have strontium as +1. We're going to take the strontium plus, turn it into strontium 2 plus, doing a reaction called the second ionization energy. And ionization energies, if you remember, are always one electron at a time. And it takes 1064 kilojoules per mole to take off the second electron from the strontium ion, or a second electron. Okay, so now we've got strontium in its +2 state as a gas. Now let's do the same thing for chlorine. Chlorine, we're going to turn the reactants into gases. Well, it's already a gas. So now we're going to take the chlorine gas and do a bond dissociation energy for it. Delta H B D E. We just talked about bond dissociation energies, but bond dissociation energies, if you remember from the lecture outline, takes an atom that is bonded and turns it into, takes a chlorine, for example, that's bonded to itself and breaks that bond. Sort of write break there. And so you start with chlorine bonded, and then you break the bond and you end up with 2 chlorine gas atoms. And this, according to our bond dissociation energy table, chlorine is 242 kilojoules per mole. And that's also on the list here. Now let's turn them into gaseous ions. Adding an electron is called an electron affinity, EA. We're adding the first electron. Oh, and I need 1 electron as my reactant to do it. I get Cl minus gas. That is delta H EA1. And it is minus 349 kilojoules per mole. This is an exothermic process because this Cl minus now has a noble gas core. And that's what separates it from all of these others. All of these other ones were doing what might be considered unnatural processes. We are taking things and raising their energy by putting energy into it. Here we're getting a little bit of energy back. This releases energy. That's why it's negative. Now, okay, we're finally ready. Our last reaction is called the crystal lattice energy. Reaction. And it's the only one, delta HCle, that we don't know the energy of. However, we're going to write the reaction. It's going to be strontium 2 plus gas plus 2 chlorine minus gases goes to strontium chloride solid. And in the lecture outline, we reviewed what this process is. And and if you now go through all of these reactions, you will find that a la Hess's law, the only things that do not cancel out are going to be the strontium solid. All right, strontium gas cancels, strontium plus 1 cancels, strontium plus 2 cancels. So the only strontium species that doesn't cancel is Sr solid. For the chlorine, Cl2 gas, well, let's see. I have 2 chlorines here and I have 1 chlorine here. So one of them cancels. I have 1 Cl minus gas on the product side, and I have 2 Cl minus gases on the reactant side. So in order to make everything cancel, I have to multiply this times 2. That gives me 2 Cl gases and 2 Cl minus gases. And lo and behold, it gives us 2 electrons, which cancel the 2 electrons here. And so the only things that don't cancel add up to the reaction. This is the world's largest Hess's law problem. Well, it's not. It's not in the Guinness Book of World Records or anything. But we do need a piece of paper to continue the problem. If you'll remember Hess's law works like this. You can add up all of the reactions to get the bottom reaction. And you can add up all of the delta H values to get the bottom value of delta H, which is minus 828 kilojoules per mole. And I did miss one other thing. Remember, if you multiply any reaction times 2, you have to multiply its delta H times 2 as well. So the new thing here is putting it all together in this specific way in what's called a Born-Haber cycle. What is not new are the reactions. Well, maybe sublimation is new. But we've looked at ionization energies before. We've looked at bond dissociation energies before. We've even quickly looked at what an electron affinity is, though there were no trends in electron affinity that I asked you to know. I did ask you to know the trends in ionization energy. Anyway, so now all I'm going to do is, when I added up all my reactions, I can add up all my delta H values. And that looks like this, 148. And I'm leaving out my units since they're all kilojoules per mole. Plus 549, plus 1064, plus 242, minus 2 times 349. I guess technically I should say plus a negative, plus delta H crystal lattice energy equals minus 828 kilojoules per mole. So this is all of these reactions, delta H values added up. And it may not be the world's biggest Hess's law problem, but it's certainly the largest Hess's law problem we do in this class. But once you get here, this is your X. And it's all algebra. It's actually hardly even algebra now. It's going to be 148 plus 549 plus 1064, times 1, plus 242 plus 2 times minus 349, plus times 349 minus equals. So I get 1305 plus delta H crystal lattice energy equals minus 828. Flip this negative over to the other side, and I get that delta H CLE equals minus 2133 kilojoules per mole. And that is the answer that we're looking for. And let's come back to the problem statement. It says, given the following information, construct a Born-Haber cycle showing all reactions and their energies to determine the lattice energy for strontium chloride. Here's all the reactions written out, and here's the determination of the crystal lattice energy down here at the bottom. Also include how the reactants and products cancel out, just like I've done here. That is a Born-Haber cycle, and the point of this is that we get an idea of the bond strength for strontium chloride, and the bond strength for an ionic bond is called the crystal lattice energy. So this is an estimate of the bond energy or bond strength of the ionic bond in strontium chloride. And the crystal lattice energy process right here is imagine taking a strontium atom far away from two different chloride atoms far away. That's what we mean by the gas phase. And then bring them together to form the solid. And that's why it's an estimate of the ionic bond strength. You're starting with atoms that have no interactions you're starting with ions that have no interactions, and they're in the gas phase, they're very far away. And you're bringing them together and allowing them to form the ionic bond. Anyway, I am happy to take any questions.